All righty. Hello, everybody. How we doing again? Hopefully good. It should be the weekend for y'all as we're looking at doing just a few more applications that involve curve sketching and particle motion. So we're going to walk through some of this stuff here and see how we're going to do. Again, a lot of this we already know. It's just spending more time dealing with some more of the applications. So that's all I kind of wanted to look at today. So here we go. We'll come back and take a look at those in a second. All right, friends. So to begin with, we have this graph. It's the graph of the derivative, and I'm asking you, first of all, a few different questions. So go ahead and pause the video, give it your best shot of what you're doing, and then we will come back and we'll take a look at it. All righty. So first question that came up, and let's see what you guys came up with. Is it continuous? Now remember, I already told you that this is the graph of the derivative. And since there's no breaks anywhere on the derivative, that means it's differentiable over the entire domain. Since it's differentiable over the entire domain, it is continuous. So since f of x is differentiable from -6 to 10, then it is continuous from -6 to 10. All right, because again, the rule we have here is differentiability implies continuity. And since I told you it was differentiable at the beginning, then it is true. All right, and now we kind of looked at these a little bit last class, and hopefully you guys found them a little bit enjoyable. Maybe you didn't. We'll find out here. Is it increasing? So remember, increasing is when the derivative is positive. So I'm gonna, every place I see positive values, I'm going to go ahead and color it red. Every place that is a negative value, I'm going to go ahead and color it green to help me kind of figure out these questions here. All righty. So where it's red, that's where it's a positive derivative, and therefore that's where it's increasing. So we can actually go ahead and write a little bit about that then. All right, let's see here. We could say f of x is increasing from, what is that, -6 to -2 and 1 to 4 because f prime of x is greater than 0 from -6 to -2 and 1 to 4. So turns out it's increasing on those domains. Wherever this is green, that's where it was decreasing. So let's go ahead and write ourselves a thing about decreasing. What we got going on there? Let's see here. F of x is decreasing from -2 to 1. And what is that? 4 to 8. And 8 to 10 because f prime of x is less than 0 from those same values. -2 to 1, 4 to 8, and 8 to 10. All right, next up. Relative maximum. That is when our graph goes from positive to negative, a positive derivative to a negative derivative. So positive derivative to a negative derivative, or from red to green. Turns out right here, that's not the color I wanted. Whoop, let's try that again. Right here, I have a relative max. So let's write about it. When in doubt, write about it. F of x has a relative max at x equals -2. We can't write it as a point yet because we don't know how to find the y value associated with this yet. because f prime of x changes from f prime of x greater than 0 to f prime of x less than 0 at x equals -2. Apparently, that is too big a line. So there we go. All right. Now we have a point, a relative minimum, when our graph goes from a negative derivative to a positive derivative. Now, notice we do have a random value on here, right here, where the graph goes from negative derivative to negative derivative. So that's nothing. There is nothing going on there. And except for, like you guys probably already remember, that would be a just a point of inflection. But we do have ourselves this point right here where the graph goes from a negative derivative to a positive derivative. Now I want you to think about that. What's that point I just came up with? That was another time where I went from a positive derivative to a negative derivative, isn't it? Turns out then, we actually have two of them. So we need to go back and amend our answer down here. Yeah. So, and we also have another one at x equals 4. Number 2. But we only have one relative min. So no harm, no foul there. We'll go ahead and throw that up here. All right, let's see what we can do with that here. F of x, let's make that orange. F of x has a relative minimum at x equals 1 because f prime of x changes from f prime of x less than 0 to f prime of x greater than 0 at x equals 1. All right, so we are able to interpret this derivative to answer some things about this graph for us. Okay. All right, well, let's clear it all out then. And now let's kind of go work the other side here a little bit. Whoop. Not what I wanted. I need that to be white. There we are. All righty. Now, let's determine when f of x is concave up. So f of x is concave up when the derivative is greater than, or when our second derivative is greater than 0. Or another way to think of it is when our first derivative is increasing. So when is our first derivative increasing? I'm going to draw all the places where the first derivative is increasing in red. There we are. And all the places where it's decreasing, that would be when it is a second derivative less than 0, and that would be when it is concave down. So again, we can write about it. Whoop. All right. F of x is concave up from 0 to, what was that, 3? And we also have it from 6 to 8. Because f prime of x is increasing from 0 to 3 and 6 to 8. Now, I could talk about the second derivative. That would have been okay, but since I don't really actually ever calculate the second derivative, I'm going to keep it in terms of the first derivative. So instead of saying the second derivative is greater than 0, which is what happens this is when my second derivative is greater than 0. And that's usually what we would have talked about. But since I'm not actually ever calculating the second derivative. I'm going to keep it in terms of the first derivative to help me out. Okay. All right, let's keep going here, friends. All right, concave down. Whoop, right there. F of x is concave down from -6 to 0, 3 to 6, and 8 to 10, because f prime of x is decreasing. That's when our second derivative is a negative value from -6 to 0, 3 to 6, and 8 to 10. All right, last one, our points of inflection. So this is when our second derivative changes signs, or in this case here, when my first derivative changes direction. So that happens at all these cusps, 1, 2, 3, and 4. I have 4 points of inflection on this problem. So again, we will write about it. Points of inflection at x equals 0, x equals 3, x equals 6, and x equals 8, because f prime of x, I can't just say f double prime of x changes signs for all of them. I have to actually be specific since I'm talking about increasing and decreasing. Changes from increasing to decreasing at x equals 3 and x equals 8, and decreasing to increasing at x equals 0 and x equals 6. All righty. So now we have, again, one more time where we're interpreting information just based off of our first derivative graph. All right, well, hey, let's keep going here a little bit. Let's do a little bit more. We're going to actually look at now some particle motion a little bit more now in terms of what we actually know based off of our relative extrema. So we can be a little bit more specific on things. So I want you to use first derivative and second derivative lingo when it is needed. Go ahead and pause the video and see what it is you guys can come up with for all this stuff. All right, let's see how you did. First up, the velocity. Determine the equation for velocity. The velocity is the first derivative of our function. So we're going to go ahead and take the first derivative of that. Whoop, there we are. And that would be at 3t squared plus 6t minus 24. The equation for acceleration, friends, that is a of t here. And that is the derivative of v of t. And the second derivative of position. So again, just like we've dealt with before, nothing really has changed here. So we have 6t plus 6. All righty. So determine the velocity of the particle when t equals 3. So we're just going to take 3, and you guys plugged it in here. I didn't give you any units, so we're not going to put units at the end of our answer here. No reason to. So 3 times 3 squared plus 6 times 3 minus 24 would be a whopping 21. So the velocity is 21 units. Units per time. We don't know what the units are, the time is, so we'll just leave it be. Acceleration would be units per time squared, but again, we don't know the unit or the time, so not to do anything with it. So the acceleration now is 3. So if I plug 3 in here, 6 times 3 plus 6, which would be 24. Determine the average velocity. Now remember, the average velocity is slope. Instantaneous rate of change is derivative. Average rate of change, which is what velocity is, average rate of change is slope. So I'm going to be dealing with the slope from 10 to negative 10. So I'm going to literally be plugging them in. So x of 10, find the slope of that position, and x of negative 10 equals 10 minus negative 10. So just finding the slope at that point, and when you guys plug that in, you guys would have came up with a whopping 76. The speed of the particle at t equals 10, that's the velocity. So speed at 10. The speed at 10, that is the absolute value. Remember, speed is velocity without a direction, or velocity is speed with a direction. You can take you pick what you want. So we're going to take the absolute value of that velocity of 10. So plug 10 into your velocity equation, take the absolute value of it, and you end up with 336. All right, why don't you guys, if you haven't had a chance to kind of work through these yet, all right, or maybe you had to change a couple things, why don't you guys go ahead and pause the video here real quick and take a chance to work on these other 3 one more time. All right, let's see how you guys did. I'm going to change colors just for the fun of it. Whoop. Is it speeding up or slowing down? The particle is speeding up at t equals 3 because v of 3, the velocity at 3 is greater than 0, and the acceleration of 3 was also greater than 0. The velocity and acceleration are both positive and both negative, and it's speeding up. But if the forces are acting against each other because they're different signs, then it is slowing down. So determine when the particle is moving to the left from negative 10 to 0. All right, so now this is one we're actually going to kind of go back in time and do a little bit of our derivative stuff here. So particles moving to the left when our velocity is a negative value. So the particle moves to the left when v prime of t is less than 0. All right, so that tells me now I'm going to go ahead and take my derivative. I'm going to set it equal to 0, and I'm actually going to go ahead and try to solve it down here. So I've already got my derivative up there. I'm going to play with that a little bit. So I said what I'm going to do. I'm going to do my work here. So 0 equals, well, where was that? 3t squared plus 6t minus 24. And let's see here. Oh, so that would be, if I factor it, I get 3 times t plus 4 and t minus 2. So at t equals negative 4, my velocity is 0, and t equals 2, my velocity is 0. Now, by the way, that doesn't mean that the particle is changing directions. The particle doesn't change directions now. All it means is that it just stopped. It might keep going the same direction. It'll change directions. If I were to have asked you, when does the particle change directions? Now you would end up doing a first derivative test. So we're going to still need check our intervals anyways, just to figure out when our particle is actually going in a negative direction. So we have t equals negative 4 t equals 2. So when it's moving left, it's going in a negative velocity. So I'm going to pick some random values here again just to help me out here. So I'm going to go, I'll pick t equals -5 so I can check my velocity there. I'm going to pick t equals 0 so I can check my velocity there, and t equals 3. Just going to check our velocity. When is my velocity a negative value? All right, so now we have velocity. In this region here, I have a positive value. That means it is going to the right. If I plug in 0, I found out the velocity in this region was less than 0. That means it is going to the left. Now I could actually say that the particle changed directions when t equals -4 because it went from right to left. Positive velocity to a negative velocity. And if I plug 3 in there, I get another velocity greater than 0. So it wouldn't have changed directions at t equals -4 and t equals 2 because of the velocity being equal to 0. They changed directions because our velocity changes signs. So, but coming back to the problem, when is our velocity going to be going to the left? Looks like it's going to the left between -4 and 2. So now we said what we're going to do. We did the work. So when we're done, got to come back and say what we found here. So let's say what we found here. Particle moves to the left because our left from -4 to 2 because v prime of t is less than 0 from -4 to 2. Determine the rate of the velocity. Ooh, and that's an interesting question. Notice what they say here. Determine the rate. So rate is a derivative. The rate of the velocity. So they want me to find the derivative of velocity. Well, friends, we know what the derivative of the velocity is. That is acceleration. So the rate of the velocity, that would be the derivative of velocity. What they're really asking for here is acceleration. So here we go. We're dealing with acceleration here. So what is the acceleration of 5? And that would be 6 times 5 plus 6. Boom. All righty. Got 2 problems done. We got 1 to go, friends. 1 to go, and then we will call it a night. Call it a night. So again, we're just doing more applications and a lot more applications that deal with graphing. So let's go ahead and start here for a second. I'm going to have you guys take a look at just the first half. Let's see, what do I want to deal with here? Left, right, nah. We're going to go for the whole thing here. That'll be fun. All right, why don't you guys go ahead and pause the video here, and then we will talk about it. All righty, here we go. Velocity. This is a velocity graph. So let's just go ahead and mark it up a little bit like we did here. Velocity is positive, real quick, when my graph is above the x-axis. My velocity is negative when my graph is below the x-axis. All right. So just so we have that kind of clarified here. All right. Now let's go ahead and take a look at some of these things we're looking at in general on this graph. Determine the velocity of the particle at 2. So we find 2 right here. And here, right there is my point at 2. So what is that velocity? That would be 1. So v of 2 is 1. Since this is the velocity curve, not the position curve, this is the velocity curve, whatever that value is, that's my velocity. Acceleration is the derivative of velocity. So since acceleration is the derivative of velocity. And remember, what is derivatives related to? They're related to slope. My acceleration is going to be the slope of that line, of that full line segment. So A of 2, well, that would be the slope. So from this point here to this point here, what is the slope of that line segment? All right, so we got there 1, 2, 3, 4. Is that 5? Looks like 5 to me, friends. All right, so, and that is -2. So -2. And this up here is 1, 2, 3 to 4. So -2 minus 4. 5 minus a -1. That would be the acceleration. And again, we can clean that up. On the AP test, I wouldn't have cleaned it up. I would have left it alone. But we can clean it up. Acceleration would be -1. The slope of that line segment is -1. All right, well, I'll tell you what. Let's go ahead and try some of these others right here. I'm going to block some of these out to begin with. Whoop. Undo. Just gives us a little more room to write here. All right, so it's determine when the particle is moving to the right. So the particle is going to move to the right when my velocity is a positive value. So when does that happen? That's the red values. So the particle moves to the right from -3 to 3, and that would be, oh, is that 9 out there? 9 to 11, because the velocity is greater than 0 from -3 to 3 and 9 to 11. Apparently I can't spell either. And I guess we probably need to make this a little bit larger. There we go. All right. So the particle moved to the right from -3 to 3 and 9 to 11. When is it moving to the left? Same idea, but this time it moves to the left when my velocity is a negative value. So here we go. Let's try this one here. The particle moves to the left from, oh, what is that, -4 to 3? And, oh, 3 to 9, because the velocity is less than 0 from -4 to -3 and 3 to 9. When does the particle change directions? Well, when the particle changes direction, when I have a relative extrema. I don't really care what type. I just need to know that I have a relative extrema. So changes directions here. Because the velocity went from negative to positive. Velocity goes positive and negative here. So there's another one, and here as well. So it changes directions 3 times. The particle changes directions at t equals -3, t equals 3, and t equals 9, because b of t changes signs at t equals -3, t equals 3, and t equals 9. Got a little bit right out there. So we got to go just a little bit up. Do that right about there. All righty. Okay. Well, now I think we're ready to deal with these guys. So I'm going to erase this here in a second, and we'll come back. So we'll erase these here. Let's see here. Whoop. And we'll take a look at some of these guys. We'll just grab our little box here. Let's move it on over here and give ourselves a little more room to write. Determine the velocity of the part if the velocity of the particle is increasing or decreasing. So is the velocity increasing or decreasing? Now remember, if it's increasing or decreasing, that means we are talking about acceleration. Okay, so what is the acceleration? What is the rate at t equals -2? So we come over here to t equals -2. We are going to look at the rate t equals -2. My acceleration is a positive value. So that means, and you can see the positive value because the whole line segment is going in a positive direction. Okay, so that means my acceleration is a positive value, therefore my velocity is increasing. Notice I didn't say speeding up, I said increasing. There is a difference. Increasing or decreasing is just acceleration. Speeding up or slowing down is a comparison between the two, between my velocity and my acceleration, and if they have the same signs or not. So we would say the velocity of the particle is increasing at t equals -2 because the derivative, or we can just say because either one of two things, right? V prime of t is greater than 0, or you can say v of t is increasing at t equals -2. I would probably because I'm dealing with just the derivative itself. Personally, I probably would have used the increasing one, but both would actually work for you. I probably would have used this one right here. I probably would have gone this route here since I'm dealing with just that velocity graph. Average acceleration, all right? So average acceleration, now be careful. If I ask you for average derivative or average rate of change, or try this one, average velocity would have been slope of position. So average acceleration would be slope of velocity. I'm going to write that again here just so we all have that there. Let's see here. We can erase this. Average velocity is slope of position, while average acceleration is slope of velocity. All right, so I'm going to take my endpoints here, and I'm going to just essentially just find the slope of it here. I can do that. All right, let's see. Whoop. All right, so the average acceleration. That's going to be, and again, I'm going to use my squiggles. So the v of 11 minus v of -4 all over 11 minus -4. So what is v of 11? That's 1 minus a -2 all over 15. So that's 3 over 15, or 1/5. That's my average acceleration. And the last part, determine the velocity of the particle at t equals 11. Well, that's an easy peasy one. Velocity is just that value right there. So the velocity of 11, that's just that point right there at the end. And that would be 1. By the way, just for the fun of it, what if I asked you for the acceleration at 11? Could you do it? Why don't you pause the video and tell me what the acceleration of the 11 would be? All right, let's see how you did. Notice if I wanted the acceleration, it's on that line segment. So what I'm really asking you here is, what is the slope of that line segment? So here, this value right here is 5 and -2. So what I'm really asking you is 1 minus -2 and 11 minus 5. So notice the average acceleration is different than the actual acceleration itself at 11. There we go. All right, so friends, just a little bit more applications with curve sketching and some more just time hanging out with and playing with this idea of particle motion. So you guys are watching this on the weekend, so I'll see you on Monday. We'll talk more about this and we'll get ready to finish up. We got one more video after this where we talk about optimization. Take care.